So this finishes the discussion for friction on a box kept on an inclined plane as the angle of inclination keeps on increasing. So in this case, only linear motion was happening. So now we introduce objects which can rotate as well. So the next topic is friction on a sphere which is moving on a rough inclined plane. And because of the friction of this inclined surface, the sphere in this case is going to rotate in an anti-clockwise direction. So just like in case 1 where there was a box kept on an inclined plane, in this situation we are going to discuss what is the impact of angle of incline on the acceleration of this object, as well as how much friction will act on the sphere depending on the angle theta. Now, there are two terms which we need to understand in a lot of detail: rolling without slipping and rolling with slipping. Because in exam questions, these terms will be used extensively. And depending on the case, the approach to solving questions will differ. So let's start. What is meant by rolling without slipping and what is rolling with slipping? Rolling without slipping is nothing but pure rolling. Before we get into this concept in a lot of detail, let's have a look at a video. Over here, you can see that there is a person throwing a bowling ball and hitting the pins. So the ball is going forward as well as it is rotating. But can you figure out, is the ball rolling without slipping or it is actually slipping? If you look at the video very carefully, when the person throws the ball, when it makes an contact with the surface, is it slipping or is it not slipping? If you have played bowling or whenever you do it the next time, please notice about the behavior of the ball as it is going along this path. Is it slipping or is it not slipping? Let us try to understand how to differentiate between whether the rolling is without slipping or rolling with slipping. So have a look at a video where we have a wheel, and let's say the wheel is rolling on a horizontal surface. So now watch, it is very easy to observe that the wheel is not slipping on the surface. It is just rolling. And this kind of motion is called pure rolling. Or in other words, this is rolling without slipping. On the other hand, what is rolling with slipping? So have a look at this video on the right hand side. It's a bowling ball. So watch as the person throws the bowling ball, just observe the type of motion which the ball is doing. So the moment the person lets go of the ball, observe the motion. So once more, so you can see the ball is not rotating that much, but it is slipping initially. Initially, there is a lot of slip and very little rotation. But as the ball reaches upon this point, so let's say somewhere over here, the ball starts to rotate without slipping, which is pure rolling. So let me repeat, initially the ball was slipping, but at a certain stage, the ball starts to do pure rolling. So rolling without slipping and with slipping, it is easier to understand if you look at the two videos. Now, how to solve questions based on rolling without slipping and with slipping. So let's understand the concept. Imagine we have a wheel which is moving forward with a linear velocity v, and also because of the friction of the ground, let's say this sphere is rotating in a clockwise fashion with an angular velocity omega. And since the sphere is rolling without slipping, this is an example of pure rolling. And in such cases, linear velocity and angular velocity are connected with the formula, which is v is equal to r omega. So in the exam situations, be careful. We can use v is equal to r omega only if the question has specified that the rolling is being done without slipping. On the other hand, once the wheel starts to slip, so have a look at this image where the wheel is moving forward with the velocity v, angular velocity is omega, but imagine that the ball is doing forward slipping. This actually means that the ball is moving forward faster than it can rotate. So in such cases, the value of v is greater than r omega. So v is greater than r omega. And if we see this expression, that means the object is slipping, but in the forward direction. As opposed to this, we have the backward slipping. In this case, the forward motion of the ball is lesser than the rotational motion of the ball. So in this case, v will be less than r omega. So imagine a situation if you are sitting in a car and all of a sudden the driver puts on the brakes. He slams the brakes very hard. So what is going to happen when the brakes are on? The rotational motion reduces a lot, but the linear motion still continues. Remember the Newton's first law, an object in motion will want to stay in motion. So if the car is already moving, but you have slammed the brakes, which means omega reduces a lot, but the speed will take some time to reduce. So at that exact moment when the brakes are applied, then the car will slip. To be specific, it is the tires in the wheels which are going to slip in the forward direction. So that is forward slipping. In that case, the forward speed of the car will be greater than r omega. And we are going to use these concepts while dealing with the next topic, which is acceleration of a sphere moving down an inclined plane. So imagine we have a ball which is rolling down an inclined plane, which is rough. Since friction exists, so the ball is also going to have rotational motion. So the ball is not only having linear acceleration, but also angular acceleration. And earlier we had discussed there is a relation between linear and angular acceleration given by A is equal to R alpha, and a similar expression exists between linear and angular speeds, which is v is equal to r omega. But before we apply any of these expressions, it is important for us to remember both of these expressions are only valid under a certain assumption. And that assumption is these expressions are true till the time friction is enough to prevent slipping. So that means the sphere is doing pure rolling. Or in other words, the sphere is rolling without slipping. And that is why in the exam questions, whenever you see this term rolling without slipping, only then we can use these expressions A is equal to R alpha and V is equal to R omega. Please note the inclined plane is rough, which means it is having friction. So let us now get into what is the magnitude and direction of friction acting in such cases. So in case one, which is a sphere rolling without slipping, let's read friction acting on the ball, which is rolling without slipping, is static in nature. Now, if you recall, static friction is the friction acting on the object when the box or any object is not slipping on the surface on which it is kept. In case one, we have seen that the wheel is rolling but without slipping. The wheel is not slipping on the surface. So, no matter how fast the wheel goes, the friction acting on it will be static in nature. And what about the direction? So, this is the diagram, pure rolling, velocity forward, and omega is in the clockwise direction. How to find the direction of friction in this case? Since the ball is moving to the right hand side, so friction, of course, can be thought of going in the backward direction. But just to check whether this direction is right or wrong, we will take the help of torque. So, what is the direction of the total torque acting on this object? Since the wheel is rotating in a clockwise direction, so the net torque will also be in the clockwise direction. And now, if you imagine the forces acting on this wheel, it will be mg acting downwards, normal reaction acting upwards, and friction acting backwards. Torque due to normal reaction will be 0, and torque due to mg will be 0. As we have discussed earlier, the torque of that force which passes through the axis of rotation, torque will be 0. But torque due to friction will not be 0 as friction is not passing through the center. And if you recall, how do we find the direction of torque? We'll try to create a circle using this green arrow, but that circle should be centered at the center of the sphere. So the circle will be going in the clockwise direction. Hence, the torque of this friction is clockwise, which is exactly what we wanted because the net torque acting on the sphere was also clockwise, which means the direction which we have defined is correct. The static friction is acting in the left side. Now, coming to the second case when rolling is being done with slipping, here friction acting on the ball which is rolling with slipping is kinetic in nature. Static friction, if you remember, is a variable. It goes from 0 to a maximum value, but kinetic friction is constant. Kinetic friction or dynamic friction is applied on the object when the object is slipping on the surface. Here, this case is either forward slipping is happening or backward slipping is happening, but friction will be kinetic. And now let us look at the direction. In case of forward slipping, where we saw the forward motion was greater than r omega, in this case, since the wheel is slipping in the forward direction, so friction will try to oppose it. So kinetic friction will act in the leftward direction. But when it comes to backward slipping, the wheel is trying to slip backwards, which the friction will try to oppose. And that is why in this situation, in the backward slipping situation, the kinetic friction will be acting in the forward direction. And that is why to solve the exam questions, you need to be careful. First, we need to check is the rolling happening without slipping or with slipping. If the rolling is being done without slipping, friction is static. Otherwise, it will be kinetic. And this finishes the analysis of friction on a sphere which is rolling on a rough inclined plane. And now let us summarize both the situations side by side. Friction on a box kept on an inclined plane. So earlier we had seen if the block is kept on a rough horizontal ground, but if the block is at rest, friction will be 0. But now, if the same box, let's say, is kept on an inclined plane where the angle of inclination is theta, and in this case, if the block is at rest still, the friction acting on it will be static. As the box is not yet slipping on the incline, the direction of static friction will be acting up the incline. but the magnitude of that will depend on this angle theta. If we keep increasing the angle theta, the value of static friction will keep on increasing. And the direction of static friction will act up the incline. But the magnitude of that will depend on this angle theta. If we keep increasing the angle theta, the magnitude of static friction will keep on increasing. So in case 3, let's say we have increased the angle of incline, but still, let's say the box is not moving, block is at rest. That is why friction will be static. Direction is up the incline and magnitude now in this case will be greater than in case 2 because the angle of incline has been increased. So the magnitude of static friction keeps on increasing depending on the angle theta. But friction cannot increase forever. There is a maximum upper limit to how much the friction can increase. That is called the limiting friction. So that is why if we consider a critical angle theta, when the block is just about to move, in that case, the friction acting on the block is limiting friction. And limiting friction is nothing but static friction, but whose magnitude is maximum. And limiting friction is given by the formula mu times the normal reaction. And now we consider the last situation if the angle of incline is greater than this critical angle. By the way, this critical angle was the angle of repose. In the last case, if the angle theta is greater than the angle of repose, then the block definitely starts to move. And since the block is actually slipping on the incline, we'll say the friction acting on it is dynamic or kinetic friction, which is going to act up the incline. That's the direction, but the magnitude of dynamic friction is a constant, as opposed to static friction, which goes from 0 to a maximum value. Now, let us repeat the same analysis for a sphere or a wheel which is rolling on a rough inclined plane. We start with the simplest situation where the ball is rolling on a rough horizontal surface. And assume, let's say, the wheel is rolling without slipping, which is pure rolling. And since the wheel is not slipping on the surface, the friction acting on it will be static and the direction will be backwards. And now, let's say the same wheel is kept on an incline, and because of the angle of inclination, the wheel is, of course, going to roll down because of gravity. So the wheel is not only going to have linear acceleration, but also angular acceleration. In this case, you can see omega is in the anti-clockwise direction. Even in this case, let us assume that the wheel is rolling without slipping, so pure rolling. Since there is no slip, friction acting on this wheel will be static, same as in case 1. Now let's say if we increase this angle theta further. So case 3, the theta angle is much greater than case 2. But here also let us assume that the angle of inclination is not that great that the wheel starts to slip. Which means even in this case, the wheel is rolling without slipping, pure rolling. No slip exists, and that is why friction acting on this wheel is still static. But the key factor is the value, the magnitude of static friction will keep increasing depending on the angle theta. But like in the previous case, static friction cannot increase forever. There is the maximum upper limit, which is called the limiting friction. So even in this case, let's say if we increase the angle to a critical angle. In this case, let's say the ball is just about to slip. In this subcase, the friction acting on it will be the maximum value of static friction, which is called limiting friction. Direction is, of course, up the incline. The magnitude of this friction will be maximum as opposed to all the cases discussed so far. Remember the angle of repose. In the first case, that angle of repose was the angle, the critical angle of the incline when the block is just about to move. In rigid body mechanics, if we have a wheel rolling on an incline, so that critical angle when the ball is just about to slip on the incline, that is the angle of repose. Now, let's say if we increase the angle even further. So consider the last situation when the angle theta is greater than the angle of repose. In this case, definitely the ball is rolling with slipping. And since the ball is slipping, kinetic friction or dynamic friction will come into the picture. And the wheel in this case is forward slipping. So the slip of the wheel is in the downward direction, acting parallel to the incline. And friction will try to stop it. That is why the direction of dynamic friction, even in this case, is up the incline. And this was the entire summary. How do we figure out friction depending on the angle theta? And before solving any exam questions, please revise this concept over and over again as it's a very tricky concept. But if you understand it once, then you will not be doing any mistakes while solving the questions.